So we have exponentials and logs. Back to the basics, right? So go back to algebra 2, go back to trig. The log of a to the x is equal to y. And I'll write that over here so we have it like as a reference as we go through all of these problems, because you're going to be referencing that formula and our other formula pretty much the whole day. So we have log base a of x equals y can be transformed at any time to a to the y equals x. The converse of that is also true. If you have a to the y equal to x, you can turn it into log base a of x equal to y. Similarly, e to the x is equal to y in the same way that the natural log of y is equal to x. Because we know that the natural log of x is x, because we know that ln of e are inverses. So that's where this property kind of comes into play. So it says to evaluate the following. So we have log base 3 of 81. So that's kind of like saying this is equal to y, but I want to know what is y. Well, I don't anticipate you guys to know what logs are, but I would anticipate that you could say, okay, 3 to the y has to equal 81, therefore y has to be 4. Because 3 to the 4th is 81. So you use that property to be able to rearrange the terms. Same with log base 25 of 5. That's like equal to y. That's the same as saying 25y has to equal 5. How do we get 25 to equal 5? Square root or 1/2 power. First part, easy. Okay, log base 10. So 10 to what power is 0.001? Well, 0.001 is a fraction, and you know this. Yeah, so how would you get 10 to be 1,000? 10 times 10 is times 10. Yep. So if it's in the denominator, it just needs to be a negative 3. The next one, not a trick. However, the natural log of e to the negative 100 is simply but ln of a should be under than ln of x. So we have something called the change of base formula. And the change of base is another way of changing or manipulating log base a of x with ln's. So the natural log of x over the natural log of a is the same thing. Now your calculators are a little bit fancier than when I was in school, and now you can actually put in a log to any base. So when I was in school, we had to know that ln of x over ln of a is the only way to do a log that had a base other than 10. So logs have these properties, and hopefully we remember them, that says addition is really the same as multiplying their insides. So if they have the same basis and they're being added, the log base A of m plus log base A of n is equal to the log base A of m times n. So that's log base 4 of 64. So again, if I want to know what that's equal to, I need to know 4 to what power is 64. Great. Same base, but subtraction becomes division. And 80 divided by 5. Yeah. Two to what power is 16? So log is 2 of 16 is 4, or this original log is technically 4. Okay, that's all in that natural log. Just like I can condense, I can expand. And when we get to derivatives, expanding takes away the chain rule or a quotient rule. So it's helpful to know how to expand a natural log because it allows me to avoid a chain rule or a quotient rule. So the natural log of all of that can be rewritten as the natural log of the top minus the natural log of the bottom. But then it's also helpful to recall that if the entire bottom is to a power, that power becomes a coefficient. So we can't do that here because x squared is not part of it unless I changed this to the natural log of 3 plus 2 natural log of x, which you can do. Why would changing it to the natural log of 3 plus that 2 log of x be helpful? Well, ln of 3 is a number. The derivative of a number is always, so it gets rid of it. So that's why we would want to break the 3x squared up. Minus 5 ln x plus 1. You cannot break up the x plus 1 because that's addition inside the natural log, not multiplication. So multiplication becomes addition. Addition does not become multiplication. In reverse, the first thing you do is bring the coefficient in. So if you're doing it in reverse, you bring the coefficient in first. So you have ln 3 plus ln 8 to the 1/3. Then you multiply. And we know that 8 to the 1/3 is really just the number. So 2 times 3 is really so coefficients in first. And then addition and subtraction to multiplication. So you get ln x, y, a over z. You can solve using those same properties in reverse. So if we have ln x equals 5, how do I get rid of an ln? Okay. Example number 2. E both sides. Solve for x. Now, the pickiness in me will split that probably into two fractions and break it down. Make some stuff positive, like I'd say -1 over 2 here plus 5 over 2. That's just like okay, you cannot e both sides if you have an ln on both sides. So you cannot e both sides if you have an ln on both sides. So we need to, in example number 3, use those properties of logs to get the ln's together. So the ln 2x plus 1 plus ln x equals 2. Now adding two ln's is like multiplying, so you'd have ln x times 2x plus 1 equals 2. ln 2x squared plus x equals 2. Now you can e both sides. That's how you solve it. You subtract the e and then do quadratic formula and you're going to get this. And then if you have an e and you want to isolate the x, how do you do that? You can't E until you move the 7. Or sorry, you can't LN until you move the 7. So you have to isolate your E. So you have to isolate the E and then LS. We're okay solving all of that and doing all our properties? Yes. Great. So it says, which of the following pairs of graphs could represent the graph of a function and its derivative? So going back to graphs of derivatives and functions, we know that if a function is increasing on its original, that the derivative has to be positive. If it's decreasing on the original, then its derivative has to be negative. So in this first example, this is increasing. Its derivative has to be positive. Is that true? Here, increasing, positive. No, because right here, this graph is not positive, that is negative. So therefore, 2 is false. And in 3, the graph is increasing, positive, decreasing, negative. So 3 also holds true. So D would be the correct answer. 1 and 3 could represent graphs and their derivatives. So that leads into today, because as you see, I labeled 1 and 2 as y equals e to the x. What you should notice is that if y equals e to the x, its derivative is also, yes. So everybody loves the derivative of e to the x because the derivative of e to the x is e to the x. Now don't get me wrong, it'll change if it's to something other than x, but derivative of e to the x is e to the x. So the derivative of the natural exponential function is e to the x. So remember that putting d dx in front of something tells you to take the derivative. So if I had find d dx of e to the x, that means you are finding the derivative of whatever follows it. And again, the bottom tells you what you are deriving with respect to. There's not a top variable because there's no y equals in this case. If it was y equals e to the x, then it would become dy dx equals e to the x. No y here. What happens though if that power, the e to the x, is being raised to as something other than x? Well, what's nice is the derivative is still e to the u. However, we have to also then multiply by the derivative of e to the u. So it's sort of like a combination power rule, chain rule, mixed together to make this like new rule. Another way of writing that would be d to the x of e to the u equals u prime times e to the u. So that du dx represents u prime. So sometimes you'll hear me say e to the u times u prime times e to the u. Same thing, because again, multiplication is commutative, therefore it does not matter the order with which you write that. So, find the derivative. So this is important to do after chain rule, after product rule, and all that, because we have in this problem a product rule. So dy dx equals the first times derivative of the second. So this is my new problem. So it's e to the negative x times the derivative of negative x. So derivative of negative x is simply plus the second times derivative of the first. So I get negative x squared over e to the x plus 2x over e to the x. Technically, these are like terms with like denominators. So it's really like negative x squared plus 2x all over e to the x. Y equals e to the tangent of x. So again, your derivative is e to the x times derivative of that power. Derivative of tangent is, so that's, if you put it in a nicer order, secant squared x e to the tan x. And then you also like, oh, today is so nice. No? That's a quotient rule with a chain rule with an e to the x. So dy dx equals ODI. So bottom times derivative of the top. Derivative cosine is. And then you have to multiply by the inside angle. So derivative of 2x is minus the top times derivative of the bottom. So e to the 3x times derivative of 3x, which is 3, all over the bottom squared. Clean it up. What do you have that occurs in this problem? We have a PCF. E to the 3x occurs twice. So we're going to factor that out. And in all technicality, your denominator is e to the 3x squared. So if you can factor out an e to the 3x and the bottom is e to the 3x squared, I can cancel an e to the 3x. Making my final answer negative 2 sine 2x minus 3 cosine 2x all over e to the 3x. Sometimes, when I showed it to you as e to the u and u prime, sometimes it's helpful to write down what u is outside of the problem. Especially for something like this, because you have negative 3 over x, which is really like negative 3x to the -1, right? So its derivative is -3 times -1 times x to the -2. So it's just a little messy if you're doing that in the midst of the problem. So if you treat it like e to the u times u prime, that allows you an opportunity to kind of clean this up off to the side. All I want to look at for today. Unfortunately, I was running out of problems, and I didn't have a chance to print you an E problem. But what I want to do is give you a little bit of textbook anyways, because I want to do some implicit and chain rule review. So like tomorrow when you come in, we'll go over a little bit of chain rule, go over a little bit of implicit, talk a little bit about these, and then